So, Chapter 11, Voice and Video over IP. So, Chapter will start out talking about some of the terminology, talking about voice over IP and video over IP. So we'll talk about that a little bit. Then it kind of jumps into some of the details of voice over IP and as well as video over IP. Honestly, it's not something that really interests me all that much. It's not to say that it's not something that's extremely useful, because it is. That's certainly the direction that networks are going. So if that's kind of an area that you're interested in, certainly I would encourage you to look into it in a little more detail, because it is an area that you can get good at and kind of make your own little niche. Talks about voice over IP and video over IP signaling and transport protocols, and then finishes talking about quality of service issues, which are particularly relevant when we talk about video and voice over IP, as well as things like gaming and things like that. So some of the terminology: IP telephony, or referred to as VoIP, or voice over IP, refers to any network carrying voice signals using the TCP/IP protocol. That can be either over a public or a private network. It really doesn't matter. Most of the time, it's going to be over the public network, though, the internet. We've got similar services that can also occur using other protocols or other networks. ATM, for example, voice over ATM, DSL, voice over DSL. But certainly VoIP is what we tend to hear most of the time. Data connection types carrying voice over IP signals: T carriers, ISDN, etc., etc. So internet telephony refers to voice over IP specifically across the internet. That's why we tend to hear about that the most, because that's what most of us use. The big advantage to that is that it's widely available and it's cheap. Access to the internet is really relatively cheap, so we tend to want to take advantage of that whenever we can. We can also have private lines that carry VoIP calls, which also can be effective and economical. The advantage to using VoIP over private lines is it gives us the ability to control some of our bandwidth. So we can dedicate bandwidth, and as a result, we have better quality of service in those environments most of the time. Once we go public, we go out to the internet, we have less control over our end-to-end communication. So we can run into some of those types of issues with that situation. Non-data applications on converged networks: we can send faxes over IP, we can send television signals over IP, we can video conference, stream video, and webcast. And the rest of the presentation really kind of talks a lot about these three right here. You want to stick around? It's a good presentation.
Oh, I have class.
Okay. Multicasting refers to when one node transmits the same content to every client in a group. This is kind of a special case of a broadcast message. It's where essentially the server sends out one single message, and all the various clients that are part of that multicast group are able to receive that same signal. What makes it really unique is it's not an individual signal that's sent to each individual client. It's one signal that's sent out that all the clients can receive. The reason that distinction is important is it saves bandwidth. So if you have a video that takes up a lot of bandwidth, if you have to broadcast that to each individual client, you can see where that might add up really, really quickly. Using multicasting, it's a single signal that gets broadcast and received by all the various clients. Unfortunately, depending on the type of broadcast we're talking about, in some cases we can use multicasting, in other cases we can't. So it sort of depends on our application. Video over IP, IPTV, video conferencing, streaming video. IPTV, for example, can take advantage of multicasting. It's certainly appropriate in that environment. With respect to video conferencing and streaming video, you may or may not be able to take advantage of IP multicasting. All of this can be thrown together into something that's referred to as unified communications. Unified communications is the concept that we can have a single portal, a single application, some kind of single desktop functionality that brings it all together. Allows us to communicate via email, fax, voice messages, all in one application. And if you've ever had a chance to play with something like that, it's really pretty neat, because you have one place to kind of have everything there all together. Anybody seen an application like that? Played with anything like that? Maybe, what did you end up using, or what was your experience with it?
We use ShoreTel. They use voice over IP. They also have some video over IP and stuff like that.
That's what I was familiar with ShoreTel at Eastern New Mexico University. They had just converted over to voice over IP, and it was really a pretty neat application that they had. You had what looked pretty much like a standard telephone that would sit next to your computer. Your phone would ring, your computer would pop up and say, hey, it's this person. It was really just a neat system that they had. Let's see. Significant voice over IP implementation reasons. Lower voice call costs, especially if you've got a lot of long distance costs. You can certainly reduce your costs significantly. Obviously, you see Vonage commercials all the time. For personal use, Skype, I mean, you can call all over the place for free. So, new and enhanced features and applications. So, there's all kinds of stuff that you can do depending on what your organization needs. If you've got the software developers and you've got the inspiration to be able to, you've got a need for a particular application that does something with your voice communications or fax, etc., you can write the application that you need. And it allows for centralized voice and data network management. So you see this convergence of data communications and telecommunications together into one functionality within an organization. So what happens is, instead of having to maintain two separate networks along with all the various personnel, all the training that goes with that for a datacom network and a telecom network, you see that converged into a single department within an organization. Obviously, that leads to some reductions in staff, but they have a single network to concentrate on. That has pros and cons. The organization can save money. That's great. You also have the issue of, if your network goes down, you've lost everything. So there's pros and cons to it. Voice and data configurations. You can have traditional telephones that hook up to voice over IP networks, and we'll talk about that a little bit here in just a second. You can have TCP/IP voice over IP telephones. You can have your computer set up, with a microphone, speakers, and you can have a mixture of all of the above. So analog telephones, if we hook those up, you can use a traditional telephone with a digital voice over IP connection. You have to convert the signal in some way. Why? Because voice signals are analog signals. We've got to convert those analog signals into some kind of digital signal so we can transmit it across our TCP/IP network. So we've got to have some kind of codec to be able to do that. That's what the responsibility of the ATA is, the analog telephone adapter. So it might look something like that. You can look at some of the different connections down here. You've got your power phone lines, so your traditional RJ11 connectors, your traditional 4-pin plugs that you would see for a regular telephone plug, and then you've got your network connections up here. And they kind of threw in a sample network diagram there. IP telephones transmit and receive only digital signals. Now, they don't really talk about it that much in the book, but the reality is you still have to capture those voice signals to begin with. You still have to convert those voice signals back into audio so that the person on the receiving end can hear what's going on. So there's still a conversion that's happening. It's just happening directly in the telephone rather than with some kind of separate adapter. So the voice is immediately digitized and issued in a network packet form. Requires a unique IP address. It's a node on the network, just like a computer is, just like a network printer is. It has to receive its own IP address. So you've got a telephone line, or excuse me, a telephone that looks, as far as the network is concerned, just like a computer that's on the network. It's got its own IP address. Most of the time, the phones will look pretty much like a regular telephone. They don't show it here. No, they don't show one there. Yeah, there's one. So it looks pretty much like a regular telephone. A lot of times, though, you'll have a nice large display on them, though, because they can receive an awful lot of information. It's not like a regular telephone in the sense that there's very little information that gets transmitted, like caller ID. With an IP telephone, you can transmit a lot of additional information. You can monitor, for example, a directory. It can store everything in a directory that's being transmitted for the organization, much like a contact list. You can that you might have in Microsoft Exchange. Go back just a little bit. Okay, let's see. IP telephone's popular and unique features. You may have web browser screens where you can look up a web page. You may have a corporate directory, for example. It's on a web page. It has a series of numbers. If you've got a smartphone, a lot of times if you go to a web page, you can simply click on a phone number. It automatically dials it. You do the same thing with a smartphone, or excuse me, an IP phone. Connected to a user's PDA, speech recognition capabilities, busy line instant message options. So really, again, this is what I was talking about earlier. A lot of this depends on the ingenuity of your organization. What kinds of applications do you need? You could write an application to work with your IP telephone network to really get some of those features if you happen to need them, if they're not currently available. You can also get mobile IP telephones. Will actually kind of move around quite a bit. Unlike a traditional telephone system in an organization where you would plug up in one office, that office number was associated, or excuse me, that telephone number was associated with that specific physical location of that office. With an IP telephone, though, it's a little bit different. You unplug that telephone, that IP telephone, and go into another room, into another office, into another building on the same network, plug up, it's still got that same IP address associated with it. So that phone number rings regardless of where you plug it in on that network. So that's a real plus to it. It's also a negative. The question becomes, where do you have to do the programming? When somebody moves offices or when they change phones, if their phone crashes and things like that. So in the book they kind of talked about that as being an advantage, yes and no, as far as that. Let's see, we already talked about signaling. One of the downsides as far as IP telephones, they need an electric current to run. That's, you know, if they lose power, then they're not going to be able to function. That's a little bit different than the traditional telephone network. The traditional telephone network uses an electrical signal as a carrier signal to be able to send signals down the wire. So in a sense, they're self-powered. It's kind of like power over Ethernet. It's a self-powered signal that operates your telephone. IP telephones don't traditionally have that, so unless you have some type of backup as far as a UPS or something like that, or you're using power over Ethernet, if you lose power, your IP telephones are going to go down, so that's certainly an issue. Let's see. That's all I was going to talk about there. Okay, so soft phones refer to IP telephoning through our computers themselves. So sound card in the computer so we can get audio out, a plug up for a microphone, some type of a video with a mic built in, something like that, so we can get audio in and audio out. And that allows us to be able to use our computer just like we would a telephone. Obviously, we have to have minimum requirements. We have to be able to run the software to be able to communicate. We've got to have some type of client. That's going to be what represents our, our dial pad, our contact information, etc. Digital telephone switch communication, full duplex sound card, and then some type of microphone or speakers. Everybody's used Skype or something somewhere. Okay, so an advantage, let's see, is they have some sort of graphical user interface. We're all familiar with GUIs, so they tend to be very intuitive as far as how we use them. Tend to be very customizable, so that's good. Difference between IP telephones and soft phones. Soft phones have versatile connectivity, voice over IP for traveling employees and telecommuters. In other words, once you set it up on your laptop, you've got it with you. Take it with you, go wherever you want to go, plug up to your network where you get into a hotel room, and plug up to the network where their wireless system's up and running, and you can connect to that. You're good to go. You can connect from wherever. Soft phones have convenient localized call management, so call tracking features, so you keep track of things like dates and times, things like that, which helps to simplify record keeping. So there's an example of something you might see. Again, if you've used Skype before, you're certainly familiar with it. So that's voice over IP kind of in a nutshell at a relatively high level. Like I said, it is something that you're seeing a lot of, especially large organizations, try to move to because of the cost savings. It definitely places demands on the network that weren't there a few years ago because we're putting stuff onto the network that tends to consume a lot of bandwidth. So it's something to be aware of. But if it's something that you're interested in, I would certainly encourage you to go out and try to learn everything you can about it because it is something that you could kind of distinguish yourself from others if that's kind of your specialty. Talking about things that consume a lot of bandwidth, voice obviously consumes a lot, video consumes a lot more. They said Cisco Systems estimates by 2011, 60% of internet traffic will be video traffic. That one, that struck me as kind of interesting when I saw that. So I Googled it, and obviously that was a 2011 statistic. The results that I found said that they were anticipating by 2012 now about 50%. I saw another one that said that that felt that Netflix was consuming approximately 22% of internet bandwidth in North America. 22% from one company. I mean, I use a lot of Netflix, I really do, but not 22%, that's a lot. Anyway, requirements for prediction to come true, continual price drop in video over IP hardware. Well, you know, that I think is certainly happening. That's something that's indicative of the computer industry as a whole anyway, so prices drop on hardware, so that's certainly certainly something that's happening. Networks must further augment capacities and reliability. I think you see that too. You can look at the cellular market as an example. They're constantly trying to upgrade their networks in order to be able to push out content that people want. I've got Netflix on my phone. I mean, you can certainly access all kinds of stuff because of increased capacities. Video over IP services categories, streaming video, IPTV, and video conferencing. And a lot of times these all get thrown under a capital V for video conferencing as a kind of an overarching term. Video over IP transmission includes digitizing audio and video signals. So, streaming video, the simplest among all video over IP applications. Most of us have heard of it. Video on demand is another class, and then streaming video is another class. They all fit within the umbrella of capital S, streaming video. So this small s, streaming video, is just a category or subcategory of this overarching streaming video. So streaming video. Video issued live directly from the source to the user. We're going to send it out live. The content may not be edited for distribution. Viewers must connect with the video stream when it's issued. So you think of it as an example, you try to log in to monitor what's going on in Congress and in the House of Representatives or in the Senate. Whenever they're broadcasting, that's when you have to be logged in. It's not being recorded for later content, later access, so that's certainly one of the downsides to it. One of the plus is you have the ability to multicast that particular signal. So you only send it out to clients that are requesting it. So to manage the bandwidth that's being used. Video on demand benefits, though, content viewed at the user's convenience. So you have the ability to log in, start the particular video that you want to watch whenever you want, whenever you need to. That is a unicast message, though, so your bandwidth requirements go way up in that type of environment. But it gives you the ability to pause a show, rewind it, fast forward, watch it again, etc. And they threw that up there. I'm not really sure why, because I don't know that it really helps convey that much information. Considerations for streaming video: the number of clients receiving each service. And remember, it's a point-to-point video over IP. It really depends on the type of broadcast that's being sent. Again, if it's being streamed, you can multicast and as a result save on bandwidth. If it's being used like video on demand, it's going to consume an awful lot of bandwidth. Also depends on the network type classification, private versus public. Remember, in a private network, we can control our bandwidth much better than we can if we're utilizing the public network. With the public network, we're really kind of at the mercy of not just our routers and our transmission lines, but all of those that exist from our point to wherever it's being broadcast to or received from. So all those public routers and transmission lines. Most streaming video takes place over public networks, thanks to Netflix. Okay, so another class is IP television. And this is something that's occurring right now that we tend to not see that much. It tends to be pretty transparent to us as individual users, but it's definitely occurring in the marketplace. Telecommunication carriers and cable companies using the IP infrastructure to be able to deliver content to you as individual users. You end up receiving a cable box or a Verizon box that looks just like any typical cable box, but in a lot of cases these are actually boxes that are receiving signals over the IP network. Basic elements: the telephone company or cable company accepts video content at a head end and serves to provide management services, video channels assigned to multicast groups. So you might see something like this, where some kind of a main office that's referred to as their head end, where they're going to receive all these various signals. Those signals may be coming in via satellite. They may be coming in across to the airwaves, just like you would receive them with an antenna. They may be local feeds, cable access, for example. And they combine all those together at their head end, and then they're able to transmit them across their network. Now, their network may consist of fiber optic, hopefully, if you're Verizon. In a lot of cases, that's the case, at least in this area of the country. They could be WiMAX. They could be across cable lines. It really depends on the company that's doing it. The advantages of IPTV is it allows them to multicast, which, again, saves on bandwidth. So it's simple to manage content delivery. You do run into an issue of local loop capacity issues. Now, if you're the cable company or you're a telephone company that's offering these services and you're multicasting these messages, in the traditional model, if you will, of broadcast messages over the airwaves, the way your television basically worked is your antenna would receive every signal that was being broadcast. Your television tuner would then filter out, when you tune into, say, channel 5, would filter out all the other channels, all the other frequencies that are being broadcast, and only pick up channel 5. It's still receiving all the channels. It's only focusing on that particular channel that you're tuned to. So you might start to think, well, that's a lot of bandwidth. We're sending out a lot of signals. One of the ways that they end up handling that is by transmitting only the content that's ordered. So essentially, basically what happens, instead of sending out every signal to every single customer, your set-top boxes, if they will, sends data back to the cable company or back to the telephone company that tells them which particular group, which particular multicast group that you want to belong to. And that's the channel that it ends up receiving. As you change channels, it sends that signal back again to again receive the next multicast group that you want to belong to. So it's a way for them to be able to save bandwidth and yet be able to offer you an awful lot of different channels. Let's see. I'm not really sure why I kept that slide. If you hadn't noticed, I kind of went through some of these slides because they put in a bunch of slides. So your set-top box might look something like that. Obviously, it's going to depend on the individual customer or individual company that you're receiving services from, whether it's Verizon or AT&T or any of the other telecommunication companies or cable companies that are out there. That's what allows you to decode the signals, manage those delivery of services and things like that. And then video conferencing. Video conferencing can occur usually either in unidirectional communication or through what we normally think of as video conferencing, or bidirectional or full duplex. So in unidirectional video over IP services for video conferencing, we're basically only receiving a presentation. You might think of that as a webinar or a webcast. We're receiving video from one direction, they're sharing content with us. Video conferencing that we typically think of refers to, or that we normally think of, refers to where we have it going back and forth. Skype, for example. But usually when we talk about video conferencing, we're normally thinking that there are more people involved or more groups involved. So unless you've paid for the version of Skype that allows you to do that, we're usually talking about something that's a little bit more complex. Benefit is it allows for real-time communication, cost savings, and convenience. We don't have to go to the airport and fly to another location if we have a business meeting. We can video conference. There's some examples in YouTube. If you take a look, Cisco, for example, has some YouTube videos that show some of their capabilities. They have some very expensive rooms, for example, at various locations where they have a conference table that is literally butted up against the wall, and they have screens against the wall. And so you sit up next to this, and these big screens, it looks like, and on the other side, it looks like there's tables right there and chairs. So it gives you this appearance, this feeling as if you're conferencing with these individuals right there, when in fact they're somewhere else. There's another one where they show an individual that's halfway across the world, and it allows a 3D conference to occur, a holographic conference to occur, in which a person is, I believe it's John Chambers, is the CEO of Cisco, is presenting a presentation on stage, and as he's presenting, his co-presenters halfway around the world and walks up to him and talks to him while they're up on stage. The reality is it's a holographic image that's being projected. So it's really an interesting little video to watch. So it allows you a lot of cost savings and convenience in terms of not having to fly around the world to conduct those types of meetings. Some of the uses of video conferencing: telemedicine. You may think of an example of that. Well, how might video conferencing be used to deliver telemedicine? Pardon? Surgery, treatment. Think about the locations around the world where doctors are probably pretty sparse. You don't have a lot of doctors. But you may have other people that can render assistance. Well, if you can get a doctor via video conference to be able to see a patient, to be able to work with a patient, work with that person that can help that individual there, they can give a doctor's opinion, a doctor's aid, a doctor's guidance to be able to hopefully deliver some type of aid. Teleeducation, judicial proceedings, surveillance. So there's a lot of applications of video conferencing that are occurring more and more often, and it'll get to the point to where it becomes second nature, that we don't even really see video conferencing as anything special. There are dedicated phones for video conferencing, and these phones have actually been around for a very long time. Relatively recently, they've started to standardize with respect to protocols and things of that nature, such that you have much better interoperability from one brand to another. Some of the very early ones, you had to have exactly the same phone on both ends to be able to communicate. Obviously, that created a real issue. The phones were expensive, and you had to buy one for everybody that you wanted to be able to communicate in that way. So how do we get these various signals, video signals and voice signals, across our private networks, across our public networks? Well, through various signaling protocols. There's a lot of protocols that are required to be able to send these communication signals back and forth. Our signaling protocols are really nothing more than information exchange. What kind of information? Well, handshakes. How are we going to communicate? How are we going to manage the sessions? How are we going to control the connection and the disconnect of calls? Things like that. With early voice over IP, we used a lot of proprietary signaling protocols, and this is what I was just talking about. That with the use of proprietary protocols, you really get locked into that particular vendor's equipment, that particular vendor's software. And so that's something that a lot of the IT community tends to want to avoid. They want to kind of shy away from that. They prefer open protocols. So that's what we're starting to see. We start to see standards bodies that are developing and implementing or standardizing signaling protocols that everybody can use, and that increases the interoperability. So one of the main protocols is the H.323 protocol. It describes architecture and the protocols It established, managed packet switch network multimedia sessions. It supports both voice and video, and it has a variety of terms that are associated with it: the H.323 terminal, gateway, gatekeeper, etc., etc. It was codified in '96 by the ITU. Early version suffered slow call setup, so a second version actually came out. And there's a third version that hasn't been widely accepted yet, but SIP attracted the network administrator's attention. Because of this right here, it really never got the, I don't want to say support, but it never really got the critical mass that it needed to be widely adopted. It tended to be more complex, and as a result, there was this real demand for network administrators, on the part of network administrators, to get some type of protocol that was easier to implement and didn't have some of those issues. And that's where SIP stepped in. Performed similar functions, codified in '99 by the Internet Engineering Task Force. The goals were that it was really modeled on the traditional structure of the Internet. So it's modeled on the HTTP protocol, the application layer, used existing TCP/IP protocols, and was modular and specific. The problem with it is limited capabilities and limited functions. It didn't do everything that the H.323 protocol did in terms of error correction and all this kind of stuff. The way around that was what I mentioned a few minutes ago. It works with several other protocols at different layers and allows those other protocols to handle some of those issues. The real issue behind SIP was its simplicity. So because of that, network administrators tended to prefer it. So that's why you tend to see it used quite a bit. I did a Google for voice over IP phones, for example, and the vast majority of the ones that I ran across said that they support the SIP protocol. So it consumes fewer processing resources, adapts easier, tends to be more flexible. Okay, so that is the basic structure, or that's the basic protocols, the two protocols that operate between the client and the server. That's what allows those two to communicate. But the infrastructure that handles voice over IP, that handles video over IP, is similar to our email infrastructure. If you recall from our discussion about email, it's not as simple as a client and a server. We also have to talk about the transportation of data between various email servers that occur across the network, which use SMTP to be able to forward those messages. Voice over IP and video over IP have something similar, and that refers to how data goes between the various gateways. And the protocols that are used there are either MGCP or Megacode. So these are gateways that are integral converged networks. And essentially they're delivering our payload across the internet from gateway to gateway until they ultimately get to the server. Let's see, another protocol, real-time transport protocol, operates at the transport layer, or excuse me, at that application layer. And one of the things that it does is it allows us to start to identify when there's a problem with the transmission. Remember earlier I mentioned that SIP allows some of the other protocols to be able to handle some of the issues, like quality of service issues, which it does not handle. H.323 does, but SIP does not. SIP passes it off. This is one of the ones that gets passed off. And it allows RTP to be able to look at things like our destination packet assembly order. So how are the packets coming in? Are they coming in the right order? It becomes more important when we talk about voice over IP and video, because we don't want choppy video, we don't want syllables out of order, things like that. Also, it looks at packet loss during transmission and assigns a time span. The downside is it has no mechanism to detect success. That's where RTCP comes in, real-time transport protocol. Provides quality feedback to participants, packets transmitted periodically, which creates overhead. This basically allows the protocol to now detect that transmissions are occurring successfully from where they're they're sent or they're received. Let's see. RTP and RTCP provide information about packet order, loss, delay, but they can't correct for transmission flaws. So if there's a problem, you can't do anything about it. Again, it's handled at another level for that. That's where quality of service comes in. Voice over IP and video over IP or a packet switch network becomes a real issue. Again, because of the fact that we like syllables in the order in which they were spoken. It's real inconvenient for computer networks to be able to do that. So it creates an issue for us as users to be able to effectively use a packet switch network for these purposes. It creates a traditional packet switch network creates delays, disorder in terms of the packets that are being transmitted, and distortions where certain packets are received very quickly, other packets are received over a longer period of time. So that certainly creates some problems with our reception of a signal. How do we correct that? Well, we can allocate more bandwidth or dedicate bandwidth to our particular transmission. That's one solution. And then there's other techniques that we can use to try to end up with a higher quality of service. Quality of service measures network expected performance. High quality of service ends up in uninterrupted, accurate, faithful reproduction of the signal. So we end up getting a good signal if we have a high quality service. With a low quality service, we're going to end up with that jittering and things like that. And unfortunately, operating across the internet where we have inconsistent quality of routers and different bandwidths from router to router across the internet, that's certainly a possible issue. So how do we go about trying to make sure that our quality of service is sufficient to be able to communicate? Well, there's a couple of different approaches. There's RSVP, which basically is an attempt before the call is ever made to go out and reserve X amount of bandwidth necessary for that particular call or that particular video conference. The advantage to this is that it reserves that amount for the call. So you're really going to be pretty much guaranteed that you're going to have a relatively high level of service. The downside is it reserves that space, and it's not necessarily the most efficient use of that space. So it doesn't tend to be particularly efficient. It has a lot of overhead that's generated along with that. Diffserv is a competing approach that basically takes advantage of certain characteristics of a packet and the information that make up a packet, and allows you to assign specific levels or specific priorities to different types of packets. And says that a certain packet, such as a video packet, is of more value than, say, an email packet. And as a result, it looks at all of the various packets that are being transmitted and can allocate, and prioritize the certain packets over at the expense of other packets. So again, video or voice would be prioritized over email or other HTTP type traffic. Let's see. Okay, so that chapter, we started out talking about some of the basic terminology, voice over IP, stuff like that. We talked about, with respect to voice over IP, we talked about the different types of VoIP networks that we might have, or VoIP communication that we might have, where we have traditional analog telephones, where we might have IP telephones, where we might have soft phones, or some combination of those three on our particular telecom network. We talked about video over IP and three classes of that: streaming video, IPTV, and video conferencing. We talked a little bit about signaling protocols, transport protocols, session protocols, and finished up talking about quality of service, which, like I said, really as it relates to not only video and voice, but also to gaming, is particularly important, where we really have to have almost a circuit-like switch performance using a packet switch network. So that is that chapter. Was that chapter 9? I think. Whatever chapter that was. Any questions over that one?